Hi, everyone, and welcome back to the Information Bottleneck podcast. And today we have a great guest, Jonas from Tübingen. He is a machine learning researcher. Hi, Jonas.
Hey, nice to meet you. How are you doing?
Good, good. And hi, Ellen. How are you?
It's nice to meet you again, Ravid, and nice to meet you, Jonas. And I'll also just start by saying one quick thing. We were told by one of your students to mention this about you, but you're apparently a really excellent advisor as well. And we're not allowed to say who it was, but we just want to point that out. That this is a very cool advisor if you're looking right now as a PhD student. Assuming
I'm actually only hiring 0 to 1 people this year because I hired so many a year ago. So you should also probably apply to other people if you are. We can talk about that later. It's a whole thing.
Yeah, maybe we'll talk about what your thought about how to be a good advisor. Actually, I think it's interesting.
I'm not sure I know, but we'll see.
We will try. Okay, so let's start with the recent news from the recent week. What about that? Apparently, it looked that we will have a peer review for literature service and position papers on archive. What do you think about it?
It's tough, right? It's I think none of us wants more like red tape on archive, and no one wants more stuff and limitations and papers being on hold. It's all kind of annoying. It's right. It's nice as a preprint server. We just uploads things and you just get them online. But I also see Thomas viewpoint, right? Who is Thomas Dietrich is currently one of the people in the archive steering board or commission, right? Or currently organizing it. And it just gets swamped with all these terrible papers day in, day out that are kind of maybe also a bunch of them are AI generated. And his point, I think, is I see his point of the surveys that I think the median survey paper that gets uploaded to archive is so bad that you could have also deep researched it. And that's kind of I don't know what to feel about that, right? I do like good surveys. I think a good survey about ML is very important. It's because there's so many papers coming out, it's very good to have good surveys. But the median survey is not very good. It's often someone who doesn't really know the field and they just look up a million papers that are related to the keywords and then they write one sentence about each. And those surveys don't get you anything if you actually read them to understand the field. I guess that kind of level of survey has been automated away now. I don't know what you guys think about that. Is that too imposing to say that level of survey has been replaced by deep research?
I'm glad you brought up all this, and I'm glad you brought up deep research because I always talk about how much I love deep research and think it's a very powerful feature. I think there's a few other notes on this, right? First of all, you have to get accepted to a conference. A workshop is not good enough, and there's pay-for-play really bad conferences that you can get accepted to, which will technically qualify you, and really excellent workshops with, in some cases, close to 20% or 30% acceptance rates that won't get you accepted. Like a NeurIPS workshop won't qualify you, which I think is annoying for one. For two, historically, position papers are kind of a new thing, and I believe ICLR's last position paper track had a 4%, a stupidly low acceptance rate, which indicates that this is. I'm especially worried. I'll say one other thing, which is that archive is traditionally meant to be basically, people who have some connection to academia and have somebody vouch for them as being not a perpetual motion nut, all right? Like somebody who tries to be mainstream scientist. There's a website for the perpetual motion people who are upset about not being allowed on archive. It's called Vixra. And I worry heavily that changes, especially if they do changes much more like this going forward to all papers going forward, which could happen as AI generated papers kind of become even more of a problem in the next few years. I worry about websites like Vixra becoming more popular as the new real preprint place. Finally, I'll just say that there were existing rules that basically nobody ever followed because the moderation workload that archive has is already impossibly large. And one other quick thing, which is that people are connecting this to AIII or triple AI's huge number of submissions this year. I just want to point out that also China is waking up, and visa restrictions aren't really a problem for the triple AI this year due to it being in Singapore. And so there's a little bit of the whole thing of like a very large number of like pent up Chinese demand that's kind of coming out at the same time that may not be per se AI like itself like swamping. So I'm trying to say there's like a lot of stuff going on here, but you
Yeah,
covered
that's true.
good parts of it.
Right. Yeah. But what were the old rules like? Right. Like technically under the old rules, like, or maybe not the old rules, right? The archive rules, I think like position papers were never really allowed. Or like, I guess like personal opinions were never technically allowed.
Yeah.
Yeah, I agree. I think
But like most like position papers also have like some experiments, right? They have like more to them than just an opinion. Right? Like maybe an opinion is just a blog post and you could just make a blog post about your opinion.
I agree. I think like we need to position papers don't need to be on archive, but we need to just to say, okay, archive is for papers but we don't want to peer review them. It will, I think that the problem is the direction, right? That like now you need to understand how to do this peer review and like which people will do it. And like, it will take times. And we all know that peer review system is basically broken. Right. And so to add this to archive, I think it will miss the point, and in the end we will find a way to go to another place for just pause your work without any peer review, that like something that I can update over time, and that's fine that I will put some preliminary results there. Yeah. And I think it's bad. Anyway, what do you think about the new cursor, the new cursor 2 and the composer model? If you don't know, the cursor just update or release a new version, and it's supposed to be much better. They pushed to command line interface, and they also released a new model for coding, the composer, that it's something like probably some fine tune on a Chinese model. What do you think about this direction?
I think you really have to update me a bit more on. I think of course I'm really out of touch. Really, I've been using just only Claude Code the whole year. I'm really out of touch with all the IDEs. But actually, it's a bit more. It's a bit similar to that now, right?
I think I don't know. Like, people have really strong feelings about Codex versus Claude CLI and Cursor, and I agree that they can be different. At the end, I don't know. I feel that like they converge to a similar solution, and I don't think that there is some very strong leader there. But I think it's interesting. It's interesting that everyone are like that. It's really easy to take a base model and to fine tune, and even Cursor, like with basically all the data that everyone are using and coding all the time, doesn't develop its own base model, but it's taking a Chinese one and fine tune it. And also it's very I don't know like what is the word, maybe concerning or like maybe not, but that they actually use Chinese model, right? That there is no American or European really good model that you can actually use and fine tune and adjust to your own use case.
Yeah, I feel like interestingly, it's a bit better on the US side, but you still have at least you have the OSS models from GPT, and the OpenAI models, right? And you used to have Llama models in the past. Like Europe never really had anything except for Mistral a few years ago.
Yeah, and Jennifer settings.
Yeah. But those are but it's a bit rough out here.
What do you think? Do you think we will see more open source European models?
There's bigger efforts in Europe now, but it's very tough to I heard a funny quote today. There was a European Commission member that and they didn't want to greenlight this grant because the grant didn't have an accounting for every single flop. They wanted to have some attachment where every single flop that they would pay for would be accounted for.
Good luck.
Right, and one flop on this machine is I don't know, it's 1 E minus 7 euros is one flop. So it's a bit hard right now. But there's a bigger push also from Europe right now to make something like this. It's pretty tough.
But why? Do you think that it's the
but it's also it's right, it's all it's all going through public channels to public right, public HPC systems, because there isn't really a private industry that would just have these clusters, right? In the US, this just runs on all private industry. And in China, it runs on private industry. In Europe, there is no private industry, so they try to run it to the public systems. But of course, the public systems have lots of regulations and requirements. Maybe that even makes sense, right? I think it's more of a question like why there is no capital to actually fund these companies that would do this privately. This just doesn't seem to exist in Europe.
Yeah, I think.
Oh, I was just going to say there is raw compute. Like Nebius, for example, is a European, I believe Finnish, right? And they've got compute. And then, sovereign AI is a huge deal pretty much anywhere right now, where the idea is to have some domestic capability to make a model, even if it's not great. For example, Cohere, is seen as like a Canadian national security kind of thing, even if, so I think Europe will eventually get there. Wanted to quickly weigh in on the cursor and composer question. I'm fascinated by how everybody's trying to have an equivalent product in the marketplace. So what I mean by this is that the attempt to compete in the CLI space against Claude Code and Codex is interesting, right? But I still ultimately think that using LLMs or AI agents within IDEs and having a human in the loop for now is significantly better, significantly higher value work can be done. And I'll point out that when you start looking at Cursor versus its major competitor Windsurf, they're very shockingly similar in a lot of ways. And then when you start looking at, Cursor has this one differentiator now, this new model that just got fine-tuned, go take a look at its pricing. It's priced identically to Gemini 2.5 Pro. I'm sorry, I played with Cursor Agent. I did just a little bit yesterday. I was hoping it would be better. I'll take Gemini 2.5 Pro 10 out of 10 times right at this moment. So it, when I can locally, that changes things. And maybe they will release it locally and I can do the VLLM self-host and use Min-T sampling and all the other fancy stuff, right? But until then, I think it's competitive.
Yeah, but also even if you're doing that, right? If you would probably would be kind of fun. I also would be very interested in doing that, right? Or also for research would be very cool. But if you render numbers on your home electricity price that you pay to serve your own tokens, you probably couldn't get the same price that they could get. Right?
I concede to this. I concede that if you choose good cloud hosting or a good per token LLM inference service, that is cheaper.
But right. Also, they have such economy of there's such an economy of scale with these tokenomics and inference providers where I guess even Cursor is struggling. But I also think ultimately, even if they actually don't make money of this, Google might just be making a slight negative. Google might lose a few cents on every token they produce. Not cents, less than that, right? But cents on a million. Google could be fine for long-term running negative margins on serving their models that none of these companies could compete with if they serve their own models. And it's a tough market.
A lot of people who I believe semi-analyses of TPUs is correct. And given what I read about them being kind of structurally behind NVIDIA by about half a generation or so, I believe that as well. I don't believe that they can maintain their price parity without losing a tiny bit of money per query at this current time because they're not model routing, no model routing. And that's also later we're going to talk about why Anthropic is starting to beat OpenAI a bit in enterprise. And that's because Anthropic's not
now. We don't have rules. That's the fun thing here, right? But I just want to say one more thing that you ignore from the speed, right? So it looked at it's much faster than everything else. So it can be that when I code, I don't want to wait, right? I don't care about, it may be a bit less good than GPT-5 codec or a bit more expensive in a few cents. But when I code, I want very fast very fast feedback. I want to know what I'm doing. I want to not to go to drink coffee and wait, and then I need to make a lot of changes and then to wait 5 hours and then to make another bunch of changes, right? I want immediate feedback.
I don't know. I'm not sure I agree, actually. Immediate feedback is nice. I like a linter, right, and stuff that just gives me very immediate feedback on how my code is doing. But if it's something that I could write, I would just write it. And then I don't need to have feedback from Cursor or something, right? But if it's something that I don't want to write, then I'm fine with it taking 10 minutes to write that for me. And that leaves that empties out some space in my head, and I hope to just offset this to the model, and I don't need to worry about it. It's fine if it takes 5 minutes, if it takes 10 minutes. Because these are self-contained tasks somehow. But it's a different use case, right? It's you have one use case, I just have a different use case. And I also I feel like the companies are a bit I don't know, if I had one of these companies trying to like sell these coding products to people, I would like go much harder on this UX angle, right? That like some people have this kind of UX that they want and this kind of task they want. I wouldn't just do like a VS Code clone and just do the same thing all the time, right? You should try to like see what your market is and maybe like only market to the Rabbit people who really want the instant feedback and want this kind of stuff, right? Or market to the agent people who like want to like write like a spec and then send the spec off. Because I don't think those products would look the same. And they're kind of all trying to do everything and they don't really have a great idea of what they actually want to do. I don't know. What do you guys think about that?
Probably we have both, right? Probably like each company will try to go to a different direction and to sell it to different companies or people.
Yeah, but so far they're so similar.
Well, if you look at Windsurf, how they're trying to differentiate, they just merged with Devin, right? And they're trying to integrate some of Devin's deeper features as tools, right? So like a whole thing about planning what you might do before you vibe code as its own separate tool. What I've found with these agents, though, I actually tried to use one just last night to make some changes to an extremely large Jupyter notebook I have that's mostly large because it's doing agentic coding in the notebook, and thus my prompt strings are very large and take up so many tokens just for the agent to try to reason through one file that it's constantly trying to go through and do things like grep lines out. And it's just, I find it extremely not useful for most of the agent stuff to go through and do this whole update all cells according to this one thing. And then I have to end up doing it with like find and replace and all of that. But I will say that oftentimes you'll get improvement. There's this Shen Comics, if you've ever heard of them. You might have seen them even if you don't know what that is when you look them up. There's a famous one where it's a guy with a giant head who's like, I've taken a controversial new pill that accelerates my brain. And the guy responds, oh, you're smart now? And they're like, no, I'm stupid faster. So speed, oftentimes I tell people that I think that I will take a marginal increase in intelligence over significant more speed, but that's also because we often don't have on hand good techniques to convert from more tokens spent on a problem to better results, with the exception of, Chain of Thought and a few others that are kind of played out now. I know there's been a ton of recent work, like there was one called, I think, Deep Confidence, Deep CONF, that was all about like doing reasoning kind of at the sampling level where you try like 500, n number of attempts at solving the problem, but your sampler, log probs tell you when you early cut off. So it's supposed to be able to be far more efficient at the whole spend more tokens, get a better result kind of problem. And so this is where I think if you initially get it to do something useful, like in Ravid's example, where it's not like horribly, bemused by one giant file, I think that if it's correct for most of the tasks you're doing, that speed and instant feedback is very valuable. But I do find a very strong value also in getting the best possible agent. And that's my complaint with agentic coding anyway. I find I switch it on to the biggest, most powerful max mode model I can in Cursor, right? Where it's like warning me, it's like, this is going to get expensive. And I'm like, I know, right? But that's why people pay so much more money for so-called geniuses to work your high-end jobs, right? So I do that too. And then I find that one query, it's done. It used $5 in like 2 minutes and it didn't solve my problem. Like, it's just so expensive to do this stuff.
I actually have a funny story about that. I had this paper recently about like parallel sampling for these like recurrent-depth models. It doesn't matter so much what the paper's about. But in the story of this paper, I actually I wasted 1 month like this summer because I had the spec written out, like, because it's kind of clear like how to do this thing if you know how the previous paper. So I spent 1 month trying to like one-shot Claude Opus into like implementing this for me, because it's like one method. It's like one like albeit complicated sampling method that you'd have to implement, and there's like a full spec that I've written for it, and there's like you could have written read the old paper. No,
you didn't work.
Couldn't do it. And then I had to was just so frustrated. Just like one Monday afternoon, I just wrote it myself, and it was just so healing to just because you know like. You get so frustrated if you just keep on seeing the same errors and you say, that's not the way to do it. And that's also wrong. And then like you go to like 20, 30 loops of like, yes, you're absolutely right. And you never get it. And then the model keeps forgetting the old problem at the beginning and you like, didn't remember this?
Yeah.
And it's just so nice to just like, once you know all the problems, because I do think maybe I learned a bit about like what the the pitfalls were from like interacting with this model. It just wasn't very efficient. It was just very nice to just write it myself, and it actually wasn't so complicated and wasn't not so long. I don't know, but there's like so much promise in these models. I wish they would learn a bit more.
Yeah, there is all this debate, right? Like for math, right? Like if they actually invent a new knowledge, or like they solve new problems, or they just like mimic and just find the right solution in all the problems. And I think personally, I think it doesn't matter.
Yeah.
It doesn't matter if at the end, if it solves your problem. The question is, what is your problem? If it solves your problem, that's great. If not, who cares what it's doing, right?
Mhm.
And I think for a lot of use cases, it already solved the problem. But if now you have a new method in mind, or right, new idea, it's still not there. It's still like you can do a lot of iterations, and as you said, it doesn't get it.
Yeah, right. I think like some of these will just go away with like better models in better time.
Yeah, I agree.
But yeah, some things are still like, yeah, for example, like with this like recurrent depth model, right? So it recurs in depth. There was always like a confusion where like after like 5, like, or like, I don't know, 5, 10, 20 minutes of talking about this with Claude Opus, it would forget that it's a recurrent depth model. And there was like some problems with the KV caching in the sampling operator, and it would say, oh, I know where the problem is. It's an RNN. It's not supposed to have a KV cache. Let me delete the whole KV cache. It's an RNN. It's recurrent. And I'm like, yeah, I'm sorry I named it recurrent depth. That was like on me. That's my mistake. I shouldn't have named these models like that. But it's a weird like semantic problem that like the model has. That like if it forgot this and then it thought it was an RNN, like a classical RNN in the end.
Well, and that gets at the heart of two of these problems, right? So one of them is that the pre-training data set on these models is so important. The initial one, not even your fine-tuning one, where oftentimes models will have incorrect beliefs about what a modern API does. So it'll be like a 2023 or 2024 spec on how to use. Often, like Pandas's upgraded library, Polars has this problem. Models do not know about recent Polars code, and it's impossible to get them to write good Polars right now. And then you get the other fundamental problem, which I think you hit quickly on trying to do interesting work, is how your context window blows up. And the theoretical context window is often, I use a 1/10 rule of thumb. Obviously, that ratio gets better as the model scales up. So hopefully it gets closer to like 1/5 or better, right? But whatever the theoretical context window is, when you hit about 1/10 of that, that's when you start seeing significantly reduced what I call like general intelligence from the model, including exactly like that forgetfulness. And then most of the techniques we have to try to manage context are still really bad. For example, like ragging and memory and all these things are okay. They certainly help, but they are really, and what I'll say is there are ways to try to do like a medium term memory, for example, compressing many tokens into like trained prompt embeddings, which aren't really used. But there could be an attempt to sort of bridge this gap that is theoretically explored quite a bit. So I just think that these two things mega hold back AI, like certainly vibe coding, and even, you know, not carefully watched agentic coding.
Yeah, I also think it's super interesting how much of an unlock just the idea was that the model was allowed to use grep. And I think we all hate that a bit, because like sometimes the model can just read the whole file, but like chooses to like try to use grep, and then it finds the wrong keyword and never finds it. The idea of grep itself was such an unlock, right? Because it was like, oh, we can just look at the one function it needs to read. And that was like such a like hack, but it very successful, right? Very successful at getting these models to do bigger tasks, because they just don't have to read the whole thing.
Yeah, it's hierarchical context management and a hack, basically. So I claim deep research and most other awesome agentic tools right now show a really clever set of developers who have done good context management. And that's why all the people that said prompt engineering went to context engineering, but that really does deserve to be a buzzword right now.
Yeah. Okay. We really need to go to start talking about the recurrent depth LLMs, models. But one more thing I want to mention this week: the small training playbook. It's a Hugging Face blog, or like a really long blog about how to build actually LLMs, and it's really great. They are doing such an amazing work. They are doing it. They did it before, right, for a Fine Web and all these series of blog posts, and now they are doing it again, and it's amazing, right? They go over so many different steps and aspects of how to actually train the model, right? Like to choose the framework, like what kind of problems you actually want to train your own model versus fine-tuning, how to choose the data, how to clean, how to filter, how to mix the data, and how like all the different architectures, right? Like different type of attentions and optimizer. They doing really good job in explaining end to end till I don't know post training and RR and things like that. And it's so important. At the end, all these secrets, right? That no one actually know till you're doing it. And why my loss just drop, or like why the norms just explode, or things like that, that you need a lot of experience in order to understand them, in order to solve them, and no one actually tell you it like in the papers. So I think this is really important, and really shout out to all of them that did such an amazing work.
Yeah, it's really good that they're doing all this, right? And it's like, yeah, it's such a pain to actually pre-train any of these models if you've ever done that. It's just like a year of pain and like things you didn't anticipate and things not going the right way. And then it's so good to have references.
They also include in this document a whole lot of interactive tools that allow you to like visualize parameter distributions given things like model size, KV heads. Honestly, it's almost analogous to like being able to build a rocket to go to the moon. And in some ways, in terms of cost and in CapEx investment, it might actually be comparable. And if you imagine that it's almost impossible for any single human to do all of that themselves, there are of remarkably small numbers of humans being the ones who ultimately went and fought through all the things that Hugging Face painstakingly documented so carefully here. This is one of the great written pieces. And I'll point out that Anthropic has been the other ones historically that have done these ultra long, very high quality kind of like almost not books, but like mostly blog posts, mostly in the context of mechanistic interpretability. And while you'll see something on like Less Wrong that's also of this quality or up there, but just the length and depth, and oh my gosh. And it also looks like it probably wasn't even written with AI, which given the length of this and the topic matter is pretty impressive in its own right.
Yeah. And we also we
It is.
probably like we don't have time to talk about what like the recent study from Anthropic, right? That they inject some knowledge and information, and they track how the model respond, and all the buzzwords that they try to say there. But maybe next week. Okay.
Yeah.
What do we know, and why we should care about length,
Well,
recurrent layers models? Tell us.
Yeah, I feel like people can't even agree on like what to call it, right? But but I think it's just because it's such an old idea that's so fundamental that, right? You could go all the way back to like the 80s and 90s, where people actually talked about like first developed RNNs, right? Also as recurrent neural networks, with the idea that it looks a bit like the brain, that you have like a small number of parameters and you keep on rerunning them, and you keep on, for example, in the brain, right? In the brain, you actually run these like waves back and forth, and you kind of would want to do this in a neural network. And normal neural networks are very, very boring in the way that, right, it's just a fixed depth. You just put input in and you run your fixed depth or compute, you run and you get your answer out. And you run, right, if it's, I don't know, GPT-3, you run your 175 billion parameters. Maybe make a more, less of a boomer example. Anyway, you run your 20B GPT-OSS, right, you get your answer out. It takes the same amount of compute every time. But maybe a token is very easy, right? Maybe like you just finish a sentence, you just have to say the end of a sentence dot, and it's actually very easy. You don't need all this compute. And maybe there's another token where maybe it's the answer to a math question, and suddenly you should actually think about this way more, right? You should actually spend like maybe 10 extra compute on this token, then you spend on the next one. And with normal transformers, this is not really possible. And interestingly, you can also just formalize this, right? That like normal transformers are in TC0. They can't actually solve very hard, for example, graph connectivity problems, just because like they're just not deep enough. It's just not possible to like, robustly encode this kind of algorithm into a model that has this kind of depth. So you want to have more depth somehow, but you want to be deeper on demand. And so one way we actually found out to do this as a community was to do chain of thought, right? So we actually spell out in words what all the intermediate steps are. And that actually is a way to get more computational depth. And models that use chain of thought actually can solve problems that they couldn't solve in one step. Because they are also like, if you imagine them like, if you imagine the computational graph is now much longer because it can go through this chain of thought. But still, that seems a bit like, it's a bit maybe unsatisfying to me, also to many other people, right? That you have to go out of the representation space of the model to decode the next token, and then you go back into it again, you go out, you go in, you go out and again. It would be so much nicer if you can just run this recurrence, or you can run this operation just inside the model. But of course, your model doesn't have an infinite number of layers. What you do instead, right? And then the natural thing to do is to just run recurrence. You just repeat, you loop, you just reuse your layers that you have already, and you try to train a model that you can reuse its layers later to do a more complicated operation. And I think it's kind of interesting to think about, like, just in general for all these papers, because there's many of them, right? Also, like for transformers, the first thing here was universal transformers, which was a paper that actually came out very quickly after the transformers paper in the grand scheme of things. Like universal transformers, I think, was like a half a year or a year later. It was this idea of like, how would you make transformers again into universal Turing machines? How could you make them? And of course, the idea is, okay, you just make them recurrent. You just repeat layers.
Do you think this is actually better that they are not universal Turing machine? Because, this is, at least for me, it sounds something like, very theoretical, right? Who cares if they are or not? Like at the end, we want very specific thing, right? We don't want to represent and to solve all the problems in the world.
I don't know about that. I want to solve all problems in the world. But no, I do agree on that. But I think that the much more practical framing of this idea is that, like, we do want computational adaptivity. We want the model to use a lot of compute on a very hard next token and very little compute on a very easy token. Right? I think that one we can agree on. That would be very cool. But of course, then, like, the question is, like, how do you even get there? And then, like, there's like been many approaches over the years, and like studies on the small scale, studies on a larger scale, just all trying to see, like, okay, how do we train the model to get this capability? Right? Because it's a weird form of generalization. You come, like, ideally you'd want to like train on the easy problems, and then you want to generalize to harder problems. And that's not how generalization usually works from like an information theory perspective.
But why you can't, like, okay, so let's assume that we all agree that we want some dynamic allocation of resources. Okay, so why do things that the coconut style models, right? That basically you're like chain of thought, but in the representation space, instead of like generate new tokens, the chain of thought tokens, right? We said that they are like, we don't want to restrict ourselves to actual tokens. Let's just feed the representation and again, and it's very simple.
I would argue that's the same thing, actually.
Okay.
Maybe that's a controversial take, but if you think about this coconut paper, where, for example, like you have like 4 of these intermediate steps, that's not so different from running like 4 loops through your model before you get the output. It's actually almost the same. It's a slightly different architecture because maybe you have like, you use your output after the first round as like context in this, like in your KV cache for the second ones. But you could think, but these are very similar, actually, these kind of approaches, because you end up reusing your weights several times before you produce the solution.
And no, but maybe let's start to explain actually what you actually have done, right? Like, what does it mean to run it and like to make it?
Okay. Yes. Yeah. So what's another approach, right? So another approach, like, that's not coconut, that was something that we spent a lot of time on last year, was this idea that we just want to train a transformer with recurrent depth, which means that it's a transformer model that has actually it has like latent recurrent depth, which is the idea that, like, so the first layers are normal and the last few layers are also just normal, and then we carve out a big block in the middle of the transformer, and this block we train to repeat, and not just a few times. Like doing training, we actually sample from a log normal distribution of a Poisson log normal distribution. So we actually have a very heavy tail distribution that's like, sometimes we repeat this block 67 times, 127 times, right? And we train this model to make sense of that and to use that compute if it has it. And so we wrote this paper on like how to scale these kind of architectures, because they have been tried for a long time on like a smaller scale with like little mazes or like chess problems. But we really wanted to train them for language. And so we just pre-trained a big model like this for language, where we basically set up this architecture. And there's like a bunch of interesting things that happen because this setup is so deep, right? If, for example, if you have like 64 recurrences and your middle layer is like 4 layers itself deep, then you're already at like a depth of 256, right? Which is much deeper than normal models are deep. And you have these interesting stability problems, and you have all these concerns about training efficiency because you do something that's a bit like an RNN, because you do truncated backprop, where you maybe do a recurrence for like 72 steps, but you only backprop to the last 8 of them for efficiency reasons, because otherwise you have a blowing up memory. And you have all these like things, these quirks to make it work, where at the end, after doing all this, you're left with a model that actually is decent, and it has interesting properties. That's what I find most interesting about these models, that they have interesting properties. Because maybe the most interesting one is that they are good at where you expect them to be good, and they're bad at where you would have expected them to be bad at. Because these models are very bad if you compare them to like other models in pyramids or flops at knowledge. Because ultimately the model is it's a small model that just reuses its parameters a lot. So for information storage, that's terrible, right? If you want to know like who all the presidents are, like how everything works, these models are terrible for that. But if you, for example, you want to do GSM-8K or even harder math problems, right? Or you want to do like human eval, you want to do coding. Suddenly these models are very exciting. They're very good at these kind of tasks. And I think it's such an interesting like flip, because like normally transformers used to be very good at like knowledge storage. And these models are good at for like similar kind of flop calculations. These models are much better at reasoning in this kind of way. And so it's a nice reversal of that.
Did you try to actually quantify which task, like reasoning task, like what does it even mean?
Yeah, ultimately, right, like this is me saying like the model is, if you look at this more neutrally, you could be saying like this model is good at GSM-8K, or the model we trained is good at like GSM-8K, Minerva Math, Math QA, and like Mastermind. Do you know Mastermind is like this children's game from like the 80s?
Yeah.
But the model is good at that. And the model is bad at like, like ArcEasy and like all the benchmark of like MMU, all the benchmarks that are like, oh, do you know who the president was in like 1873? Not good at those, right? So that's how I just make this distinction. It's a very empirical one. I don't have a good, I don't even know, because it's also interesting, like for many benchmarks, it's not so clear like whether you're wrong because you don't know the fact, or whether you're wrong because you didn't make this like conceptual leap from what you know to be true to the fact, right? And actually, like many benchmarks are a bit like reasoning problems in disguise like that, where either you know the fact, but you could be deriving the fact if you didn't know it from other things you know, but you need to do this computation to actually take that leap.
Yeah.
I agree. In practice, it's very hard to separate what's a reasoning task and what's a knowledge task.
For me, intuitively for me, like reasoning tasks are something that like you need to solve intermediate steps. That like you can't go from the initial point to the end to the solution in one step. Like you need to solve these intermediate steps, and you need to have to calculate something over this path, and like you need somehow to track your internal memory if you want, and you need to do these calculations again and again. But I agree that like most of the time it's not clear how you can actually distinguish it, right? So math problems, it's something that maybe it's easier, and you can say, okay, so in order to solve this equation, I actually need a lot of intermediate steps, right? And sometimes I even can quantify how many steps I actually need in order to solve it. But other problems, it's not clear how to do it, and what does it mean, even generalization.
And related to this, I have a similar question. It's very popular in the world with like stable diffusion models to implement what they call clip skip, which is this early exiting at inference time at layers that aren't that very final layer. What relationship does this technique have, and what we've been talking about, to those kind of like early exiting strategies?
Well, like a lot actually, right? Like this early exiting is exactly like one half of the equation. Because with early exits, you can just not use all the layers of your model. So you can always use less compute. And that's just pretty cool, because that's like half of what I wanted before, right? It's like if the token is very easy, I won't spend a lot of compute on it. And there's also there's some like a very good paper that I like a lot is Calm, which is like a paper from like about like how to optimally early exit in T5 models. There's a lot of good work on this stuff. It just doesn't have the other flip of the coin, right? Which is like, can you also use more compute than you would normally? With early access, you can only use less compute than before. And of course, like maybe you could conceive of it like that you like train like a maximalist model first.
Yeah.
Right? But like maybe like, at least motivationally speaking, I would want something where I can do like thousands of recurrences. And then you end up with like a very, very, very large like maximal size model if you wanted to train for that maximum shape. It seems much more like mathematically elegant to train for this kind of like dynamical system, or this kind of recurrence, right? This kind of like implicit formulation of the problem. Because that's just like what I think is super motivating about these like recurrent setups is like, I'm actually a bit of an energy-based model fan in disguise. And it's related to that a lot, right? Because with the recurrence, you can also interpret it as just the gradient of an energy function. And you're just learning this operation directly. And to me, that also has a lot to do with how these models, like what kind of problems these things could solve. So, and this is something you couldn't really do with an early exit. But you could if you had an energy-based model.
Yeah, it's kind of similar to the recursive reasoning, right? Model, like the less is more paper, right? They optimize some.
Yeah, I mean, yeah, right. Like, I feel like that model is like, at least like if you heard about what is described about recurrent depth, that was like in February. And then there was this HRM paper in June or something, which is like a development on that. And now this is a newer development on that field. Because like basically like it's like you could have, I mean, I'm oversimplifying. The paper actually is like very great. It's like a lot of like details also like on how to do backprop differently. Of course, I specialized a bit to ArcAGI, so it's an encoder only model. It's not really an LLM in the classical sense, but it's all these interesting things. Also, it has these like very interesting like, dual loop structure. You don't which is like also like came a bit of this HRM paper. You don't just have one recurrence. You actually have two recurrences and they interact with each other. You have like a slow running one and a fast running one. Or I guess in the TRM way of thinking about it, you have like one recurrence in the latent space and you have another recurrence in the output space. And it's pretty exciting. It was like, there's also some other papers where people do like, just like sets of like 4 or 5 loops. But it's an interesting field. It's an interesting question about like, how would you even design these systems? Right? And we're designing like, I guess, more complicated versions of them now, but they're all super excited, to me at least. Super exciting like versions of recurrence and how would you like do this, right? Because the more you have these like structures, the more maybe you have interesting behaviors that can happen.
But do you think it's like, this is, how to say, so there are a lot of discussions now about world models and what does it actually mean and how to represent it. And so do you think this is the way to achieve world model, like to achieve like it can be memory or like something that you can actually some consistent state, or you think we can also like implement in other ways?
Yeah, I feel like the world models are really implicit here, right? It's like maybe I make this like allusion to energy-based models, but is it? Yeah, I don't know. But it's like it's maybe like a few steps removed from it, right? I think about it more as like maybe like I think the world model way to think about this is that like you have a system and you can use the system to run empirical inference on itself, right? You don't really have an explicit formulation of the system because you don't have this world model. You only have this transformer with these loops and it can do things. But by running it longer, you do a more careful inference of your current state. And that relates to world modeling, but it's like you don't have the world model in hand, actually. You just have a procedure to get you to a more or less exact inference about the current state.
I agree. I think the tiny, the less is more paper is one step through to the world model, right? And you have explicit these, right? This is like kind of like your world model, and you have a recursion on the top of it, right? So you can combine both of them.
Yeah. Just a quick thing on world models, by the way. I think that world models also bring up a desire for those other GPUs that nobody cares about anymore, that Quattro line from NVIDIA, because you want highly accurate physics simulations in your data. And that's often how people are creating the world models, is through using those simulations as verifiable rewards. And I think that Google talked about this a bit with the training of Genie, I think. And then they even get like AI agents that can take any new, environment or simulation and kind of perform in it, right? Which I'm forgetting the name, but that came out at the same time as Genie.
Yeah, but I feel like, right, but you can have like a world model of any world, right? Like, it doesn't have to be a world model of a physical simulation. Although that's a nice use case for that's new quadricards.
Yeah, I'm just mostly meaning about like the data problem, right? For getting more believable worlds, and I think solving some of the problems that you see with like Sora 2, for example. Even Sora 2 has serious issues with like physics over a long enough time span. And I've heard a lot of people talking about like simulations and trying to, because you see that so much with other stuff in RLHF, right? RLAIF is like video games as their platforms for learning them, including like Doom or NetHack. I saw many papers that did things like that, and some of them have gotten some media attention.
But do you think, did you find actually some like a method that actually did it and was much better than methods that are not doing it? It was, I know it's really cool, right? To see games and Dooms and like to train and get data from it. But did you see something very, very unique and novel that actually make a big difference? Ellen? No? Yes?
Oh, sorry. I was kind of expecting Jonas to. You're asking me if I saw things that were like very different as a result of this?
Yes, that actually make a big change. I don't know, some really huge improvement.
I mean, the fact that you could do a proper, compelling Minecraft or playable Doom, I think was a crazy improvement, especially when I realized that it was rendering faster in some cases than in, some games can. Especially, I noticed that with Blender rendering getting faster when you switched it over to Stable Diffusion as the backend. But no, I think that they haven't fundamentally solved most of their problems around temporal or spatial coherence. And I think that a lot of that will come from. I think we even had I forget their name, but we've already had a previous episode where we talked a lot about like architectures and their importance for various types of data, right? And so that's, I think, where what Jonas has been discussing with these what were can you tell me again what it was called? Recurrent.
Yeah, so I've been like looking at these like, as recurrent depth models, right? Because they recur
Depth
in
model.
depth,
Yes.
which is a bit of like it comes from like a line of papers like earlier in like 2021, 2020, like doing this for like back then for ConfNets. And if you recur these ConfNets in depth, then they can solve, for example, they can solve mazes, which is like the original motivation for them that I had with this. And actually, these models are like, those ones actually do this promise that because like you can train them on like very small mazes. You can train them on like mazes that have like 13 pixels, so like, or 13 like squares on the maze. And then they just learn like a maze solving algorithm. And you can then let them loose on arbitrarily sized mazes. So they're like 4,000, 5,000, 8,000 pixels. And then it will take a lot of recurrence to like, solve these larger mazes, but these models will solve them. And that's kind of like the promise of this kind of like work, that you could actually train on easier problems. And your model, because maybe the hope is that I have is that the model would learn not just like heuristics to solve a task, but the model actually would learn algorithms to solve tasks. And then if I would give the model more compute later, it could just run these algorithms that it has learned for longer to get an answer to a more complex problem than it has observed during training.
And was it true?
That's at least a promise. I'm not saying we're there yet.
Is it true? Does it
Right?
work?
It's a promise. It's the promise. Like for example, like for the model we trained, it's very notable that like you can't get too far out of the space that you trained it in. Like for example, the model is trained with like 16 to 32 recurrences, a bit more. Like this is heavy tailed. And then on some tasks, you can get better performance by going out with like 64 or 72, but not more than that. And it's not like the model we trained, you can just run it forever and then it solves all the math problems, even if it's like grade school math. And there's something interesting about that, right? Like you could like argue that like if you're like a maximalist, you could argue that it's the language that's wrong and like the model is just not encoding the question correctly. And then it just does a lot of computation that just solves the wrong problem. And then maybe like, right, like, because sometimes maybe like if the model misunderstands the question, then there's there's no amount of compute that you can do to fix that problem. Or you're saying that, or maybe like the minimalist position is that saying, okay, the model just has not learned a very good recurrence operation. And so it can't actually like generalize to harder problems. It can just solve this class of problems and it can solve them in the close to the space it was trained in, but it can't go far beyond that. And how to go far beyond that is still unknown actually. And maybe like language is too noisy to learn that, because like maybe for most language pre-trained data, you just don't need to reason a lot. And maybe like language is bad and hard in some way. Who could say?
But do you think so? What do you think how do you think will the future looks like? You think that like we will see algorithms like, diversity of algorithms for different problems. You will have different architectures and different solutions, or like, yeah, just get me more data and it will be better. And I don't care about anything. The bitter lesson in some sense.
I wouldn't say that that's a bitter lesson, right? But I would say the bitter lesson is that like there probably is like one way of writing down a good architecture that will turn out to be like best learned from interacting with the world or best learned from data, and then we'll all end up using that. And it could be that that's not a fixed depth transformer, but I think it's something where like either we have something that's really like, I think it's only like important in it, or maybe like I think the aim of all this like architecture fields is to find a replacement for transformers, right? Or find a system that's more scalable and that just works better and that you can just replace transformers with, at least given enough compute.
Yeah, and that's the bitter lesson part is specifically that humans need to get out of the way, right? So my understanding is that the bitter lesson, if you take it seriously, tells us we should be doing, neural architecture search or I guess having LLMs and spending a lot of time on trying to have them devise even more interesting techniques like that. And by the way, one thing I do like to do once in a while just to play with models is to take a big paper like the DeepSeek V3 paper and ask it, all right, put it all in the context and be like, show me the DeepSeek V4 paper. That's a fun one for a little bit of like speculative advancements. And you can keep doing that. I get hilarious like predictions about like quantum supremacy with like DeepSeek V10 and, okay.
They love quantum, don't they?
Wait,
Too much.
is any of these idea actually helps you, Ellen?
Well, so in terms of, proposing ideas that I think could be good if you gave compute for them, I mean, maybe, right? I mean, I think that there's a lot of existing architectures today that could be better than the transformer, including RDMs that we've just talked about that have never had their proper compute mixed with the crazy data set. Basically, we haven't done the small LLM playbook on anything except transformer architecture. There have been some limited cases with state space models that have shown a bit of promise, right? Somewhat, right? But not enough to get OpenAI to be like, all right, let's put 300 million into a training run, So I tend to think that no, but it's not fair to say that that's like an indictment of the idea of like LLMs producing novel research. I mean, we do have significant swaths of mathematicians, even notwithstanding the one guy who got misquoted recently, who are pointing to kind of the idea of real novelty coming out of these models in some sense.
Yeah, well, also just for the record, obviously, we talked about this earlier as well a bit, but I find it so hard to say like the models cannot be novel. Like that seems just false to me. At least like just like conceptually, you can certainly ask a novel math question to the model and it can solve this novel math question, even if it's just like, I don't know, like even if the domain is restricted, right? And I think like for many problems, like ultimately it's not like the model looks up these answers. It's like that it knows like enough building blocks to reconstruct the answer from first principles. And that has to imply that that there's like other questions that it can also just put enough building blocks together until it gets a solution to them. Maybe like the model is not always good enough to do this, but like I feel like it's very hard for me to say that the model will never be novel. I think it's more like there's like very few problems where you can be novel. Because right, like we are all humans, we've all done research, we've solved many problems already, like as a community. The bar is very high for like interesting and novel mathematical insights, for example. But I don't think that the models are like incapable of it. I think it's just a high bar. It's like independent of novelty almost.
Yeah, I agree.
There's also this notion of interpolation versus extrapolation, which I think is identical, basically, kind of language. But we have, intuition. I claim probably all three of us and most of hopefully a lot of the listeners have seen a latent space diagram, such as what sklearn likes to show off on their front page, those like two-dimensional plots of like a decision boundary from a classifier, right? And so we can look at a point, for example, an input query, and answer given even a reduced dimensional representation. Does the point rely in or outside of the kind of defined region of the decision boundary or latent space, which is oftentimes equivalent to saying is something interpolation or extrapolation for the purposes of the model. Now, because of how LLM sampling works, you're actually orbiting around a point. If you think about it, at every token that you're generating, it slightly modifies the input embeddings. And I claim, especially with very fancy sampling, you can definitely force it into places that are potentially outside of the defined decision boundary, which is where you get gibberish oftentimes. But I claim that this is probably some equivalencies to the question of can models be novel, right? And I'm like, which is to say, can we make a model be truly extrapolative? But I also point out, we don't know what extrapolation is until much later. Like William Shakespeare might have been somewhat a little bit famous in his own time, but he wasn't world famous, universally agreed, the pinnacle of English poetry until way later. So we humans don't even know what novelty is until way later, right? Versus interpolation, which is just a combination of existing many things, right? Potentially, like a little mix of A or B. And maybe models give us this idea to truly say that X new thing is merely just a chemical equation of 1% this and 0.1% that, and whatever concepts applied, the reconstructing of how the model could have created an output given. I've been very curious about that too, is like, can we take a paper and then reconstruct the paper in some way, like find the prompt that accurately reconstructs the exact paper a human wrote, and then what does that prompt look like? Very curious if we can do that.
Mm-hmm.
Yeah, I want actually to ask you something different, a bit different. So, as someone that did so much work about like making better models that are really novel, what is your, I don't know, guidelines how to do it, right? Because there is a huge risk when you want now, I want to train or like to develop a new model that is really different from existing ones. How to make it work? Like, do you have some recipe to say, okay, let's go on this idea, and now like after I have this idea, I'm doing these and these steps. And then like when it doesn't work, like what I'm going to do, like when I see my gradients are exploding, how you're dealing with that?
I don't know, not well most of the time. I like especially like because like in that like 1 year where we worked on this model, it was pretty tough, right? Because you can of course like you can train like 1 million tiny models, and we did train like a few thousand like small scale models or like prototypes and tried some things there. But it's very hard to scale up, and there's always surprises. And then you have a limited amount of compute, and you also have like then you spend like back then I think I spent like a month just on like some communications library in AMD, and it was all a big mess. I learned way more about like networking than I ever wanted to know, just to get back to like training this model and to like see how it would perform. And then it was ultimately like the model we trained was like a 3-shot, right? We had like 2 failed attempts where I burned like 200 billion tokens worth of compute, and then we trained the model on the last 800 billion because then our compute ended, and that's where the model ends, right? Like, but it's just about like for the large scale runs, it's just on my perspective, it's just for these new architectures, it's just a lot about metrics and about like measuring many things and then seeing what goes wrong and then trying to intervene quickly when something goes wrong, and then a lot of hope.
But
Right?
can you
I think
give me
like
a example? Okay, beside hope and to cross fingers, like what you actually look on? Like, do you have like specific metric that you say, oh, it looks promising, or like no, it's something get wrong?
I mean, I think it's always a bit best if it's a bit model specific. So, for example, like for these recurrent models, we always want to look at like we're always like validating on a validation set what the perplexity was with 1 recurrence, with 4 recurrences, with 8, 16, 32, 64. Because, for example, like if they all like just splotch together, then the model is just not using the recurrence. It's like producing the same output after 1 recurrence as after 64. How these like fan out kind of like tells you like whether the model actually is learning something that it can use at the deeper recurrence, and how much you're paying for that if you just train a model had a different profile. So we just stared a long time at these kind of curves of validation perplexity for these different levels, which was I think was a bit specific to this model. We also just stared a lot. I just stared a lot at like gradients, like what's the gradient norm of the first layer and what's the gradient norm of the last one, and how does it look there, and what's the L1 norm of the weights and the L2, and then ultimately you just accumulate lots of metrics and you just look for anomalies. And you look for like how they like, because you have some idea like what they look like for the small scale model, right? And if something's really different at large scale, like you kind of wonder whether that makes sense or whether like it's not training well or some part, or like it's not getting gradients to the beginning. And I don't know. You know, I should be more principled about this, Toby. I think I'm still learning to be more principled in every time I do this project. But it's such a hard thing because like you can be like infinitely principled and then never train anything, and you like ablate everything and you never get anywhere, or you can just like gung-ho like train something and then you just burn all your compute on the stupid thing. And there's some middle ground somewhere that you have to find. I'm not sure I'm optimized yet, the middle ground yet.
But do you think there is like kind of some recipe to identify good ideas before you actually do them?
I mean, right? Like if it doesn't, I don't know. I think like a classical sentiment is like that. Like it should at least work on a small scale as well. But for some ideas, I'm not even sure I believe them. Right? Like there's some ideas that like might not work on a small scale, but they would work on a larger scale. So I don't know. What do you do?
I think it's very first of all, yeah, it's really hard, right? And I think both of the things, both to understand like what ideas can actually work before you're actually doing it and what can scale up. I think this is so much rely on intuition, and it's something that you don't have like really good answer for that. And this is something that like really bother me because I thought about it a lot and I asked a lot of people and no one have good answer, you know. It's something like, yeah, I have this feeling, right, that it will work, and I think most of the ideas are not working, and so I don't think there is a good answer.
Yeah.
And yeah, and regarding like debugging and understanding the model, I think this is something that I feel that you first need to build, a lot of metrics, like what you care about, as you said, right? And you first need to build a lot of different metrics and to try to debug them in really, toyish examples, and only then to start to run things, because it can be very, very messy really quickly, right? And now you're waiting, I don't know, a week or 2 weeks for something, and then you understand, and it doesn't work. I think, yeah, you need to spend so much time on trying to measure basically everything before we are scaling it up.
Well, yeah, I've seen, we saw the craziest loss curves ever when we tried to do, new exotic techniques in the transformer reinforcement learning and PEFT library. I don't know what the right learning rate is supposed to be. I've seen stuff that makes me believe that I'm 3 or 4 orders of magnitude off base whenever I try to follow what like existing numbers. I don't know what's going on. I'm shocked anybody can train anything successfully. It's impressive every time it's done.
Okay, I think it's a good time to go to some questions from the audience. So each week we are trying to post and to ask people what they want to ask you. So someone asked, what are the potential dangers and complexities introduced by shifting the reasoning process from the human interpretable token space to latent space?
Yeah, that's actually something I've been thinking a lot about, right? Because so I do work on efficiency, but I also do a lot of work on safety. That's maybe even 60 or 70% of my actual working time is on various safety topics. So I've thought about this a lot. But actually, in hindsight, for this model, I just wasn't this wasn't such a concern for me, but mainly because I already don't believe that chain of thought is so monitorable, right? Especially if you look at these OpenAI outputs from actual reasoning that they're running. I don't know, did you guys see this this recent, or maybe a good example from, was it Apollo research, with these parted illusions, marinate comments? It's very easy to train these models to get a very uninterpretable COT already. And I don't think we should make alignment systems that rely on surveying the chain of thought of these models. But also right, it's also interesting, a paper that there should be no pressure on the chain of thought, which I do agree with, but also by writing this paper, now there's pressure on the chain of thought. And you can't say that you are not supervising the chain of thought and then supervise it. And it's much better to actually look at the actual activation of the model. I'm much more interested in research that actually looks at model activations, and that works for recurrent models, and it also works for standard transformers. And there's been so much interesting work, for example, this is a small digression, but we had this paper recently about lying in transformers, or whether they would choose to be strategically dishonest. And there it turned out that you can actually just see that the model is producing neurons that correspond to a falsehood, and you can make these probes, and they just classify this very well, that this is a falsehood and this is a real thing I'm saying. And now as the model, I am lying here, and here I'm not lying. And that's such a more promising approach to me than to try to monitor whatever words the model's putting out.
I agree.
Well, what do you guys?
I agree. Yeah, I think at the end, people, because it's very tempting to use tokens, because we are using language, right? We as humans, we are using language. So we say, oh, so we have this tool and we have these tokens, so let's use them. But I don't think it's there's some relationship, and it's something that you can sometimes look on it, but in general, I agree. I think the chain of thought is useless most of the time. To get real value and to understand the internal mechanism and all safety concerns and things like that, I think we can't actually use it. And the internal representation, and to find ways how to extract the internal representation, even though it's more difficult because these are just numbers, I think it will be much more useful for the long term.
Yeah, agree.
Okay, what do you think about the single scaling rule that trades model size, training tokens, and extra latent steps at test time? Does you expect that one rule to hold across autoregressive, or different families have different?
I feel that's a question that's very easy to ask, and I would also want to know the answer. And if I had infinite compute, I would love to figure it out. But it's I think it's the kind of question you can only answer empirically if you actually run those models and run all those computations. I would want to see it, But I have no idea what it would look like.
Do you believe in scaling laws, like in general? Like we talked about it last week, but what people are saying or meaning in scaling laws in LLMs is just, yeah, I'm trying, right? I'm running with this amount of compute in this configuration, and now I'm running it in 10 times more, and I see how the performance behaves, right? But
Mhm.
does it helpful at all? Does it give you anything besides, oh yeah, it goes up or it goes down?
I don't know. I do think it's very practical, and like, yeah, I think there's a lot of like, is it a scaling law? I don't know, right? There's many things that can go wrong, but like the empirical statement of like often after a certain size, if you've trained a bunch of model checkpoints on smaller compute sizes, you can empirically pretty accurately predict where you'll end up with even more compute. That I think is just an empirical statement about past models and about many architectures that this is true. It's not always so clean, right? It's not always a scaling law and it's not always perfect. It's not a physical law that this is true. It's just an empirical observation for many models that this ends up happening. And that's very helpful, right? Because often like you only have like one shot at the bigger model and you'd want to like know what ballpark you'll end up in. And I do think it's helpful for that, even though there's like, you should never like 100% trust that and like sell all your house on this empirical prediction.
Yeah, but if like at the end, if now you develop a new model, right, and like you have 5% error, so yeah, okay, what you can do with that, right? Like I can tell you right now that you will have 5% error from the best one if you're close in your configurations and settings and things like that, right? So
yeah, but for example, let's say you have like two candidates, and so you look at the scaling law, like or the fits, right? And you see that for one candidate, like it's flattening out already. So you think that like if you double the compute, it will only be like marginally better, and the other one would be it's like much more linear in compute. Okay, maybe that's actually an unrealistic dream, but right, but like that's the other one's like much better on compute scaling. And then so even if there's like a big margin of error, you see that this model looks like it will be better. I would train that one if I had the choice.
yeah, I can get it. I just like at the end now when Google want to run their new Gemini, right? Like we all know that the models in the same they will behave similarly, right? Like they will behave quite the same. The question if to be a bit better, right? So it's hard to predict. It's really hard to predict that. Okay.
Well, and
Yeah.
I was going to say that the small agents paper, or sorry, not small agents, the small training playbook shows you just how many moving parts you have. And most of those scaling laws papers say, let's take all those other, hundreds of choices you made and set them all equal and change usually one thing. And that's my problem with them is that when the next person goes and does another world-class LLM training, they make dozens of different decisions. And so I often see people on Wall Street read too much into scaling laws papers. They're meant for scientists.
Yeah, right. This is something like if you had your own stack, then the first thing probably you would be doing would be to recalibrate these metrics to your actual real stack and your real GPUs and your real like implementation. And your coefficients could be quite different, or not so much, right? But like probably like they're still kind of like logarithmic. You would not use the data from these other papers, and it's kind of like it is funny to like for the analysts to just say, okay, from this paper we see that the coefficients are X, so we think this company will be worth like Y amount of money later. It's like.
And we know greedy sampling isn't deterministic even on the same hardware if you get different GPUs. There's several papers talking about this and motivating why real determinism is important. You start talking about a crazy training run, you can have almost everything be the same and still get dramatically different results because, your silicon lottery on your 1,000 H100s was totally different than somebody else's.
Yeah, although I feel like that... I do kind of think that like those kind of errors would cancel out over a training run. That even like if you train these small scale models, then they would have these non-determinism errors, but you would be able to predict what you would end up with also for the large scale model.
Yeah.
Like sense. Actually, we train very inexactly anyway. Like we train these like funny little low precision formats anyway. Like the model is robust to many of these errors and non-determinism things. It has to be. But yeah, still, of course, like maybe you're very lucky and you get like a very good checkpoint and you don't know why you got it. I think I've heard this story from some people at some point. Then what do you do, right? Yeah.
Yeah. Okay. Let's go and let's talk about advising students. Right. So you're quite new in this area, right? Like you are like 2 years, something like that, 3 years.
I would say, yeah. Although I feel like I've got like a very good like apprenticeship advising people as a postdoc. I was a postdoc with Tom for 2 years, and Tom Gosling is a professor in Maryland. And I think like being a postdoc is a bit of like it's like a soft launch into being an advisor, because you advise people all the time, but you're not the final person that's responsible, right? There's still someone else who's actually responsible for all the important things, and you're just the fun little guy to talk to about like research and all things.
So
yeah, but still not very
how
long in the grand scheme of things.
but so how much first maybe tell us about your strategy. How do you see this role of advising students? Because it's very different from I don't know, a researcher, right? The goals are totally different. And then maybe tell us, like, did you think about it, or do you think what advisor do you want to be, or like this is you just make the decisions on the fly?
Yeah, I'm not sure I'm doing this well, but I do think that like it's important as an advisor to basically teach people to become researchers. That's the main role, is to like guide people to become their own independent researchers and to advise them on this path, right? So like maybe it's a kind of funny role, because you're trying to replace yourself. You're trying to like teach people that they don't need to talk to you anymore, that they can just do this on their own and just figure out like how to approach problems, what they should do in their career, and how they should be independent researchers, where ideally they leave their PhD and they know all this and they don't need to talk to you anymore. Maybe they still come by for tea and coffee, right? But like they don't need to talk to you anymore about like how to do these things, because they've learned them all. And I'm not right, like, and I think ultimately I haven't really thought about how to do this. I'm pretty much just being my own advisors in a way, right? Like for example, actually, there's like Professor Michael Möller, who was my PhD advisor, who is a professor in Siegen, is a small town in Germany, and from whom I have learned a lot about like how to be a researcher, also how to be a very principled or like very ethical researcher. And I think that shines through a lot from him, how I advise people. But yeah, I think it's just also like who I've talked to and who I've like, I think we definitely accumulate pieces from everyone we've ever like collaborated with. Like I think I have like some little piece, for example, from Andrew about like how to be an advisor and how to be like, I don't know, Bayesian, a small piece, right? And I think it was just we just pick all these things together and then become our own advisor as a sum of these prior advisors.
Yeah, I agree. I think like I also took a lot of pieces from my advisors, like both from Tali and Chaim and Jan, of course, and I think, and also like from different collaborators, but also like I took what I don't want to say and what I don't want to do and how I don't want to treat my students and collaborators. I think this is something that is very, very important, like there are a lot of people, without mention any names, there are a lot of people that are not such a good advisors.
Yeah, I feel like that I think the thing that I found like the worst about like my colleagues, because I think like when I was a PhD student, I always appreciated that my advisor made time for me. And I think it's such a simple thing, but like I think it's really like it's like the cornerstone of being an advisor, is just take time to talk to your students. And I try to that's like at least something I want to do. And like, and I take time, like there's like a slot every week, and then we might not meet every week, but there's a slot on my calendar every time for all the students I have, just to like actually talk to people and so they have something to talk to. Because I feel like I had some colleagues who just never saw their PhD advisor, and they were kind of just adrift doing random things and talking to random people. And then they saw their advisor like once a month or once every 2 months. And then it was like just a disastrous meeting. And then they never saw them for months again. I don't know. Before you also met these people, right? And there's some people who this can work for, but I think not many. And actually, also, I think that's also very important, is that ultimately all students are very different. And I try not to like do the same trick for all of them, right? Because people are different. And it's kind of like an advisor flaw to think that there's like, they're all the same kind of student and they all need the same kind of advice and the same kind of like structure.
Yes, I agree. I also think that like at the end, you need the advisor needs to see, not to see only their own interest, and to see like the students' interest, and like to care about their students, right? Because sometimes there is overlap between your own interests and theirs, but sometimes it's not like that. And sometimes you need to say, okay, so it's more important that they will finish, I don't know, this project, right? Even though it's not the most exciting project, and it's all their problems and these decisions all the time. And we need to remember that like we have like at the end, supervisors, we have so much power, and we really need to, to not to use it in the wrong way and to see the student before we are taking any decisions and making very bad decisions.
Yeah, right. Also, yeah, I especially like the part about like, right, like it's like I think it's so important also when people bring their own ideas to say, yeah, maybe I wouldn't have done that project, but the idea makes sense and it's your idea, so you should try it. And we'll be there all the way to like wherever this leads, right? But I think that's the only way people also become independent researchers, if they really also like, you can tell them, yeah, this is your idea, you should try it. We should try it together. We can see where it goes, right? And maybe like in half a year we find out, okay, your idea was bad, but that's fine. It was still your idea and you tried it and you learned something about like how to find good ideas. And otherwise you never learn that. You just, right? I don't want to, I think especially also like with like LLMs, with coding agents, with like AI coming up, I don't think I want people to end their PhD just being like a research drone or just an extension of myself. Like, I don't really want that. It's also like, I think I'm not the fastest coder, but I'm like maybe like middling, right? So like if I have an idea, I can just do it myself and I might just do that. And I kind of like, it's interesting to talk to students because they have their own ideas, right? And they have their own things and they're developing those, right? And that's so much more valuable for the field as a whole than just someone who just does the things I'm putting on a list, because that I could just be doing those and no one actually learns anything while just like working down the list.
Yeah, I agree. And I also think that at the end, people are doing much better work when they're actually working on their own ideas and making, the decisions, all the decisions based on their own knowledge and just taking your advice and like asking or like consulting with you, and not you just say, okay, you need to do this and this and this and this and this, and then what?
Yeah. Yeah. Right. Then you can graduate, but you're only like, you can, I don't know. You could become like a very well-paid software engineer. That's cool, right? That's like no shame on that, right? That's also like a very interesting like path in your life, but it's not like you're doing your own research after that, or you could be.
Some of my best friends are well-paid software engineers.
Yeah, same here. Same here. Also, some of my very, very good PhD friends are now very well-paid software engineers, and it does work for them.
Well, and I'll point out, I got into this AI research world starting as a, for the time, well-paid software engineer and kind of coming to this world. And I'm still, honored to ever even be allowed to host a podcast like this without a PhD, because I'm in awe of the amount of work that all the students who are working under advisors, such as both of you, have to do in order to get one of them.
Yeah, I think it's an interesting topic. Like, do we need a PhD these days in order to make a good research in LLMs? I think that I don't know, I have mixed opinions about it.
I can tell you, there's a lot of math that I think I missed out on that would have helped me, I think, if I had gone to grad school.
Yeah, I think that's definitely something like sometimes, I think it's also like the kind of applications we get that people come in and they're very excited about LLMs, right? And they have like, maybe they've done some projects already, and maybe they even come in saying, hey, I've done these 10 projects already. But like, if they come into a PhD, maybe I would rather they have done more math classes and got more like a fundamental view of the thing. Because then ultimately I think they'll have to catch up a lot doing their PhD getting these fundamentals. But this is like very person specific. Like there's some people who can just like catch up on these kind of things and just do that on the side, and it's not a big concern. There are people who come in and they're always a bit limited by the fact that they never learned this, and the kind of like contributions they can make to the field are always a bit like limited by the fact of what they've known in the past.
Yeah.
So yeah, but also like you might just like learn some math on the job. Right? Actually, I think that's like the most like engaging way to learn a new topic is to actually have to use it, right? And someone could tell you like all about like, I don't know, linear algebra back in undergrad, and you're super uninterested. But if you actually want to compute the largest eigenvalue of the neural network, suddenly this is much more exciting, and you actually figure out how like Lanczos works or some of these algorithms. That's my 2 cents on like, linear algebra.
I agree. I'm not sure that the largest eigenvalues is the most important thing, but maybe.
Hey, I like dimensionality reduction. TCA is awesome, and it got me like those like mappings and plots were very influential to me, like circa 2017.
Yeah, yeah.
I'm kidding. I'm actually like, we are using it in research every day and to analyze algorithms and representations. Kidding. Okay. Do you have anything else to add? something that you want to promote, to sell?
I don't know. I'm an academic. We're not in the business of selling things.
Now it's the time to start.
Know what I could sell? Have you heard of Tübingen? If you haven't heard of Tübingen, you should have to come visit, because I think it's really shaping up to be like a great place for machine learning research in Germany and in Europe. And we have like so many people coming in like from all over the world doing ML research in Tübingen, which is so fun because it's a tiny college town. Actually, also like, more trivia is that actually Tübingen is like one of the oldest college towns in the world. I think they have the university since the 1400s or something like that. And they had like Kepler here, for example, and people like that. So I'm very glad that they're not just like stuck in doing humanities forever, but they're also doing a lot of ML and a lot of AI now. And it's a pretty cool place. I'm actually happy to be back here.
Even though we just mentioned how Europe has some issues with like building the largest data centers or producing the largest models, I think Europe punches way above its weight, and specifically Germany and German-speaking countries, so like Switzerland, for example, crazy good quality AI research coming out of so many of the institutions out there. And I think you'll see it on, there's like demographics of where people who attend AI research conferences come from. And those countries like Switzerland, Germany, Austria are very well represented.
Yeah, per capita at least, yeah.
Okay.
Yeah, we're still tiny in Europe overall.
Yeah, but maybe in the future, right? Okay, Ellen, do you have anything you want to add?
No, it's always a pleasure to get to meet, very, very established academics like yourself and learn from you about a new model architecture.
Is this the point? Are we already well established? I feel like that's kind of like funny to say.
I think you two are.
I don't know. I don't feel that old yet.
I'm too old for all of this. Okay, and yeah, so thank you so much, both of you, and thank you for the audience, and see you next week.
Yeah, thank you for having me.
Bye-bye.